Hey guys, and welcome back to another video on the channel. Pretty much welcome back to part 2 on mathematical induction introduction. So in the previous video we took a look at these proofs up here and we went through and pretty much how to prove them, and pretty much this video is just a continuation of the problems here. Prove the following. So I just screenshotted that just to make the question make kind of sense, but the spelling's off because it had a couple of questions here. Righto, so prove by induction that this entire thing is equivalent to this. Now in the previous video, like we said, it's this entire sum is equal to this. Now when we prove n equals 1, only the first bit equals this entire bit and this bit here. Now the reason why you need to include the 1 is because if you were to try and just make this equal to this when n equals 1, you'll find they're actually not equal, because this is when n equals 0. Because if we look at this sum, we see it's going from 1 to x to the power of 2 and x to the power of n. But what we don't realize is 1 is the same as x to the power of 0. So actually it's this pattern here. So x to the power of 0 plus x to the power of 1 plus x squared, and we can see it's increasing by powers of 1 pretty much. So when you go, alright, prove for n equals 1, you need to include this 1 because that's when n equals 0. Right, so by induction we prove n equals 1 first. So let n equal 1. So you basically equivalent this and this term equals to all this. So in other words, on our left hand side we're going to have 1 plus, and then I'm going to substitute n equals 1, so x to the power of 1 is equal to, now sub in 1 up here, so you have 1 minus x to the power of 1 plus 1 all over 1 minus x. So in other words, we've got 1 plus x equals 1 minus x squared all on 1 minus x. Okay. Now at the moment it's not very obvious that they're equivalent to each other, but we can do long division on the right hand side really quickly. So I'll just label that as the right hand side. So we'll go minus x squared plus 1 divided by minus x plus 1. So minus x squared divided by minus x is going to be positive x. So we place that up there and multiply the x by this term here. So x times by minus x plus 1 gives you minus x squared plus x, and then you need to subtract this down here. So minus x squared plus x, and then we get minus x, and that's the only one that we have, and we carry the 1, so plus 1. Then we go, alright, minus x divided by minus x is positive 1. So we put the positive 1 up there, and then we multiply the 1 by all this, so 1 times by minus x plus 1 gives you the exact same thing. Then you're going to subtract it down here, and we can see it fully cancels out. So what that means is it's a factor pretty much. So in other words, this entire right hand side here is just the same as x plus 1, and we can see this side and this side are equivalent, so left hand side equals right hand side. So it's true for n equals 1. Okay, so that's the first bit. So second bit by induction is to assume that pretty much the thing is true, and we're going to substitute n equal k, where k is pretty much in the same set as n. Okay, now they haven't defined n in this problem, so I'm going to assume n is an integer. So n is some integer. That's meant to be the fancy z, like where is it? That's an n. Where is it? It's meant to be, oh, they're all natural numbers, these ones. Oh, they don't have the fancy one here. Anyway, I'm assuming it's just an integer pretty much. So assume it's true for n, well, we've seen it's true for n equals 1. Now we assume the statement is true and let n equal k, where k is pretty much a number in that same set pretty much. So I've defined n as an integer, so I'm going to define k as an integer. So you're right, assume true, let n equal k, and then you have to define k, so k belongs to the same set. Okay, that's a terrible looking z, but you get the picture pretty much. And now we just write this entire thing in terms of k, so we get 1 plus x squared plus dot 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 plus x to the k equals 1 minus x to the k plus 1 all on 1 minus x. So wherever there was an n, I pretty much just put a k. That's all I did there. Now we have to assume it's true for the term after k, so k plus 1. So assume true for k plus 1. So when we put in k plus 1, since this is a sum, you need to include another term, which is k plus 1. As we can see, it's going from x to the power of 0, so x to the power of 1 x squared, dot 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 x to the power of k, and then you have to put plus x to the power of k plus 1 because this is a sum. But on this side here, we just substitute wherever k is with k plus 1. So what we get here is, alright, 1 plus x squared plus dot 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 plus k, x to the k plus x to the k plus 1, and that's all you got to do on your left hand side. And that's equivalent to 1 minus x, and then we put in k plus 1, so k plus 1, all on 1 minus x. And this is the induction bit. Pretty much we can see, alright, this is equivalent to all of this, because that is the same as that, and they're both equivalent. So what we can do is substitute this into here pretty much. So if I can rub some stuff out and move some stuff along. So rub this stuff out, and all I'm going to do is click and drag pretty much this guy here. Now on a bit of paper you would write a new line, but because I'm on the computer I can do this pretty much. Right, so now we get rid of all this, and we try and prove the left hand side equals the right hand side. Now you can't cross cancel stuff, because then you would get 0 equals 0, because if they are equal you'll just cross cancel everything. You've got to try and make this side look like that side, or vice versa pretty much. So with the left hand side, let's try and get this guy combined with this one here. So we're going to turn it into a fraction. So what we're going to do is pretty much times it by 1. So what I'm going to do is move this actually to the side so I have a bit more room for the other term. So I want to add these together, but I can't because they're not on the same fraction. This is over 1 pretty much. So I want this 1 to turn into 1 minus x. So I'm going to times the top and bottom by 1 minus x pretty much. So technically I'm timesing it by 1. So the top bit is going to turn into, alright, let's just write this side here. So 1 minus x to the k plus 1, all on 1 minus x, plus, and then here we got k to the power of x to the power of k plus 1 times by 1 minus x, all on 1 minus x. Now I can actually add these two together because these are the same thing now. And then of course we've got the right hand side as well. So 1 minus x to the k plus 2, I'm just simplifying that, on 1 minus x. Okay. Righto, so what I'm going to do is distribute this term here. So what I'm going to get is, alright, 1 minus x to the k plus 1, plus, and then the first term here, x to the k plus 1, then minus x times by x to the k plus 1, all over 1 minus x, equals 1 minus x to the k plus 2 on 1 minus x. I can see this and this term can cancel out because they're the same thing, but one is a negative of the other. So I can rub those terms out. And here I can actually simplify this because these are like things. I can just add 1 to the power here. So I can rewrite that as minus x to the k plus 2. So I'm going to rub that out now. And what we can see is this side is exactly the same as this side. So left hand side equals right hand side, hence true for the set we've defined. So let's go k belongs to all the integers. Okay. Right, so that's how you prove that one. Obviously you would keep all your working in your book. I've just rubbed it out because I'm on a PowerPoint, and yeah, pretty much I can do what I want. Right, let's go to the next question. Alright, so prove the following by mathematical induction. Alright, so this side, this sum equals this sum. So first we've got to do is, alright, n equals 1. Now let's take a look at this first bit here. If I put in n equals 1, what am I going to get? I'm going to get 1 over 2 times by 1 minus 1 times by 2 times by 1 plus 1. So what I'm going to get is pretty much 1 over 1 times by 3. Hence why it's that term there, if that makes sense. And now if we actually take a look at it, oh sorry, I thought that was a negative for a second. So that's your first term there, okay, that you get from this bit here. And now we've got to see if this side equals it as well. So we're going to go 1 over 2 times by 1 plus 1, and that's going to give you 1 over 3, which is the same as this, 1 over 3. So left hand side equals right hand side for n equals 1. So that's the first step done. Okay. Now what we're going to do is, alright, let n equal k, assume the statement is true, let n equal k, and define k in the same set. So I'm assuming n is an integer again, so n belongs to an integer. So I'm going to say assume true, let n equal k, and define k in the same set. So we're going to have 1 over 1 times by 3 plus 1 over 3 times by 5 plus dot 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 plus, and wherever there's an n I'm going to put a k, so I'll have 2k minus 1 times by 2k plus 1 equals k on 2k plus 1. Now I'm going to assume it's true for k plus 1 for k plus 1. So now I'm going to write the next term of this sum, so I'll write all this and then I'll write another term with k plus 1. So I'll have 1 over 1 times by 3 plus 1 over 3 times by k plus dot 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 plus 1 on 2k minus 1 and then 2k plus 1. Now I'm going to put in the term with k plus 1 plus 1 on 2 times by k plus 1 minus 1 and then 2 times by k plus 1 plus 1. Okay? And then I'm going to write this side with just k plus 1 because this side's a sum and this side isn't, so it'll be k plus 1 on 2k plus 1. Okay? And then you can see, alright, this bit here in the green is the same as this bit there. So we can substitute that bit for pretty much k on 2k plus 1. So what is it? K on 2k plus 1. And that's it. Now we've got to prove the left hand side equals the right hand side. So obviously we'll turn the left hand side equal the right hand side because the right hand side is pretty simple as it is at the moment. So it's better just to combine the bigger side pretty much. So what I'm going to do is I'm going to move that closer to that and then move this all up here. Okay. First of all, I'm actually going to expand these guys here. So I'm going to have k on 2k plus 1 plus 1 on 2k plus 2 minus 1 is plus 1 times by 2k times by 2 times by 1 plus 1 is plus 3, and that's it for that bit there, equals k plus 1 on 2k plus 1. Right, so I want to try and combine these two. So what I need to do that is, alright, well, they're almost the same denominator. I just need to have a 2k plus 3 down here. So I'll put that on the top as well, 2k plus 3. So now I'm going to combine them all. So now I'm going to rub this stuff out. And move this up. So on the top bit, I'm going to have 2k squared plus 3k plus 1 all over 2k plus 1 on 2k plus 3. So what I'm going to do is, alright, I'm looking at both of them, and if they are equivalent, this term needs to cancel out somehow because they're both going to have a denominator of 2k plus 1 if they're equivalent. So what I'm going to check is, alright, what happens when I divide this by this term here? So in other words, I'm going to do a bit of long division. So 2k plus 3 divided by 2k squared plus 3k plus 1. So 2k squared divided by 2k is going to give you k. So I get k, and k times by 2k plus 3 is going to be 2k squared plus 3k minus that, 2k squared plus 3k, and all we're going to get is plus 1. So yeah, that all cancels there, so all we get is plus 1, plus 1, plus 1, yeah, that cancels, that's weird. 2k, let's see if we can factor that, actually. So if we have 2k squared plus 3k plus 1, what I'm going to check is if this is equivalent to k plus 1, times by 2k plus 3. So if I multiply this out, I'm going to get 2k squared. Then I'm going to get plus 3k plus, that'll give me 2k, and then plus 3. Okay, so they're not factorizable. Righto. So what that means is we've made a slight mistake somewhere in the working. The reason why is because it should be equal to this side here. So that means algebraically we've made an error somewhere. So what we're going to do is kind of backtrack pretty much. So just go back a couple of steps. It's okay if this does happen. The reason I'm going to include this in the video is because it will happen in an exam. But this is what you got to do. Just go back pretty much to the n equals k bit. So we know it's true for k plus 1. So n equals 1. So now we're just going to rub back and backtrack a little bit with our algebra. So we have this 1 on 1 times by 3 plus 1 on 3 times by 5 plus dot 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 1 on 2k minus 1 2k minus 1 2k plus 1 equals k on 2k plus 1. And now we're going to do the k plus 1 term, so 1, all of this pretty much, which is k on 2k plus 1 plus 1 over 2 times by k plus 1 minus 1 multiplied by 2 times k plus 1 plus 1 equals k plus 1 on 2 times k plus 1 plus 1. Okay, so I might have made an error on this side actually. So what I'm going to get over here is k on 2k plus 1. Then I'm going to get the same thing over here. So, okay, so I might have made a mistake on this side. So if I distribute that, that's going to be k plus 1 on 2k plus 2 plus, okay, so 3. Oh, maybe not. Plus 3, yep. Over here, 2k plus 2 minus 1, so it's going to be 2k plus 1. Here I'm going to have 2k plus 3 equals that. Righto, so let's see if we can do this again really quickly. I think I made a mistake on the right hand side actually, because we had k plus 1 on that side. Okay, so same thing as before, we're going to combine the left hand side and the left hand side together, and hopefully our algebra will work out. So whenever you do get an error like that, I'll keep it in the video because it will happen. Pretty much just restart the problem again and just take a bit more time with it. So go and combine these two, so go and multiply the top by k, 2k plus 3, and then 2k plus 3. So what we're going to get is, alright, 2k squared plus 3k plus 1, all on the same thing pretty much. So it's going to be 2k plus 1, and then 2k plus 3 equals k plus 1 on 2k plus 3. Righto, so I want to see if we can cancel out this following term here, 2k plus 1, because they're both going to have a denominator 2k plus 3. So what I'm going to see is, alright, is 2k squared plus 3k plus 1 equivalent to, what would this be? K plus 1 times by 2k plus 1. Because if it is, then this term will cancel with the top bit and it'll leave this remainder. So I'm going to multiply this out and see what we get. So we'll get 2k squared plus k, then we can get plus 2k plus 1. Right, so we get the top. So we can actually factorize that as the same as k plus 1 times by 2k plus 1. So we can see that and that cancel out. So we get k plus 1 on 2k plus 3 equals k plus 1 on 2k plus 3. So left hand side equals right hand side, and we're done pretty much, right? And then you can say, alright, hence is true. But the point is, if you do get to that last step and they're not equivalent, go back and check your algebra on one of the steps. I knew it was good for n equals 1, but I wasn't sure about that middle bit, so that's why I went back and pretty much checked that. Right, let's go on to the last proof for this video. So, prove the following by mathematical induction, that 7 to the power of n minus 3 to the power of n is divisible by 4 for n belongs to the natural numbers. Okay, cool. So, first of all, n equals 1. See if it's true for that. So, 7 to the power of 1 minus 3 to the power of 1 is going to give you 4. 4 divided by 4 is 1. So, yeah, it's true for n equals 1. Therefore, we're going to assume it's true and let n equal k. And we'll define k in the same set, so the natural numbers. So, assume true, let n equal k, and k belongs to a natural number. Now I'm also going to introduce another letter because we said this is equivalent to something divisible by 4. So I'm going to introduce another letter, a, and call it an integer. Because I've got to have this equivalent to something. I've got to make an equation. So I can't have an equation but it's not equivalent to something. Well, we know it's equivalent to a number times by 4 because it's divisible by 4. So in other words, 7 to the power of k minus 3 to the power of k is equal to some number times by 4. Okay? Right, so now we assume it's true for k plus 1. For k plus 1. And now I'm going to introduce another number because that's going to be divisible by 4 as well. So b belongs to another number. So I'm going to have 7 to the power of k plus 1 minus 3 to the power of k plus 1 equals to 4 times by that number I've defined pretty much. And now we've got two equations we want to try and combine together. Now, the best thing to do at the moment is, alright, what if I make just 7k the power? So I move this to the other side. So in other words, I get 7 to the power of k is equal to 4a plus 3k. Alright, so if I get that, I can kind of substitute this almost into this. Now, 7 to the power of k plus 1 is the same as 7 times 7 to the power of k. Okay? So I can change how that looks and go 7 times 7 to the power of k minus 3 to the power of k plus 1 equals 4b. Okay, so this is pretty much what I've got. So I rub this stuff out because I need a room. So I've got this here, and I've got this and this. So because I can put this into here, because I've got 7k there, I can rewrite that as 7 times by 4a plus 3k minus 3k plus 1 equals 4b. Right, so what I can do now, if I really wanted to, is rewrite this top bit, because minus 3k plus 1 is the same as minus 3 times 3 to the k, pretty much. Okay? So, and I can also distribute this if I wanted to. So in other words, I'll get, alright, 28a plus 7 times by 3 k minus 3 times by 3k. 3k equals 4b. Alright? So once I've got that, I'm going to take a look at these things. These are actually like terms. So in other words, if I just treated that as a variable, I've got 7u minus 3u, but instead of u is 3k. So in other words, I've got 4 3k here. So I'll have 28a plus 4 times by 3k, because they're like terms, equals 4b. And now I can take out a factor of 4, so I get 7a times by plus 3k equals 4b. So in other words, I've got a number that's factorized by 4 equals a number factorized by 4. So therefore, hence, divisible for all numbers. Because I was able to take out a factor of 4 out of this side. So it's true. Righto, so that's the end of the video. I hope you enjoyed this second part. If you have any questions, leave some in the comments and I'll try my best to answer them. But I hope you enjoyed.